Okay, let's get back into it. I'm trying to understand Stefano Quattrini's Breaking the Lorentz Invariance. Unfortunately, I don't think I'm going to get very far into this beyond step 3, where he says A and B are accelerated with the same proper acceleration g, because the implications of this are kind of broad. Number one, it's not an inertial reference frame. If It would be a non-inertial reference frame if A, comma B are accelerating. And if there was a situation where A and B were accelerating at the same proper acceleration, what you would have is a situation where you've got a hyperbolic arc here with exactly the same shape as a hyperbolic arc here. So we'd have your B back here and your A back here. And those hyperbolic arcs, as you go closer and closer to the speed of light, uh, will actually get further and further apart along, well, first of all, they won't maintain simultaneity, because, let's see. Yeah, because basically it's like trying to draw circles with the same radius. If I draw circles with the same radius, say, here's one. What is the radius of this thing? Maybe out to there. R. And then do something with the same R up here. It doesn't create concentric circles. It creates overlapping circles. Same thing with drawing hyperbolic arcs with the same acceleration. It's not going to create concentric hyperbolas. It's I don't know if they'll overlap. I don't think they'll overlap, but they won't. They'll actually spread out in the space, going at different velocities. Anyway, so that's probably not a greatest um, explanation, but it's among other things. There's just a lot of things wrong with the idea of taking. I mean, there's nothing wrong with the idea of taking these two clocks having the same proper acceleration at two different points in space. It's just that within their own reference frame, those two clocks are going to be separating as time goes on, as noted in what's it called, it's called Bell's spaceship paradox, but it's not really a paradox. It's just the fact that if you have two objects with the same proper acceleration, they will separate rather than staying at the same distance from each other in their own reference frame. All right, but let's go ahead and do this. As soon as the acceleration ceases at v sub naught is less than c, A sends timestamp h over c to b. Let's see if we can figure this one out and see whether he's kind of taken all this into account or not. So both of the guys are going to be accelerating from the moment that the clocks are synchronized to some moment t sub a c c. So they're going to start off instantaneous signal. I don't know when the synchronization takes place. Does the synchronization take place before the acceleration starts, or are they already accelerating when you try to synchronize them? That's kind of ambiguous in the form. Let's say they're both accelerating when the synchronization takes place. So this is going to be 0. Oh man, but they're going to call this h. I can't call that h if this guy's under acceleration. Yeah, that just the whole setup is flawed. Let's say, for the sake of argument, let's make it as simple as possible. We'll just say this guy doesn't start accelerating. Like he'll give the signal to start acceleration at proper acceleration g at the point when that light. Oh no, it's got to go the other direction, doesn't it? Okay, let's do it. Let's do it this way. We'll map this backwards. So he's going to send the signal, the initial signal, which will establish, we'll call this distance, is this distance h? Yes, this is distance h right here, from there to there. There's no acceleration going on up to that point. So we'll start the acceleration when the first initialization signal, start the acceleration g when the initialization signal starts. So that this guy will send the signal at t sub a equals negative c over h. Is that right? No, negative h over c. Yeah, negative h over c. Negative h over c. Okay. And he's actually, is he going to start? Yeah, he's going to be. No, he's not going to be. Oh my gosh. Is he going to be underway at that time? Or is he not? I'd probably be somewhat useful to just say that they're both under acceleration at the same time, but then we have to get into the Rindler coordinates. So we're going to make this a flat line here and say he's not accelerating, but he will start accelerating at 0 at the same point in time that this guy starts. And then they'll measure a time, and then we would have these, what they call it, he says after counting t sub a c c, they stop their acceleration. So if they can synchronize that so that the acceleration begins right here and the acceleration of this guy begins right there. So he decides, I'm going to start accelerating at the same point in time that he starts accelerating. Then they would be able to do this. And actually, the t sub a c c is the integral of, what is it, square root of ct squared minus x squared over c dx dt squared. Anyway, when you do that, since these are both starting out at the same time and finish, they will actually end up reaching t sub acc on their clocks. If that happened, then they would actually end up on this space-time diagram. They would end up coming to reach their final acceleration at the same moment in time. In their own reference frame, though, no. According to this, this is the simultaneity line from that event. This is the simultaneity, based on a pretty fast, or assuming this is pretty fast acceleration, and they've gotten to a significant portion of the speed of light, then the simultaneity line for these two tangents would have come up to there. And so it would be very clear from their perspective that the front guy stopped accelerating first, and then we would just continue this would continue to be a straight line from there, and this would continue to be a straight line from there. So the time at the end of the acceleration, from their point of view, the guy in front stopped first and the guy behind stopped later, which means that the guy in front has gotten quite a ways ahead of the guy in the back, which is consistent with Bell's spaceship paradox. But here he's also saying that its timestamp is h over c to b. He's sending timestamp h over c. So if he started out here at negative h over c, and then this is 0, then it's really, actually, yeah, it's probably, so he's having the time of acceleration be also equal to h over c, he would send that signal out over here, and okay, I think I'm seeing maybe some other possible construction for this. Maybe he wanted to send out a signal here at t equals 0, be under accelerate. Okay, so let me try and just is so non-specific what he's doing, which I mean is kind of like Einstein's sort of bothersome things where he doesn't really specify. So now I'm picturing something like this. The here's oh man, this is gonna be this is gonna be awful. Okay, yeah, this is okay. This is so the front observer, he sends out this signal at t equals 0. T equals 0. At the moment he starts accelerating, this guy starts accelerating at what he calls t equals h. No, is he going to call it t equals 0 or t equals h over c? He's going to, okay. Okay, I think I like the first thing better because that actually has a chance of having some kind of, co-moving parts. Uh, so, yeah, I like this a little better. He's saying, okay, this is when I stopped at t equals h over c, stopped accelerating. And I guess this guy is also stopping accelerating when t space c equals h over c. I like this version better because it at least gives some kind of hope of symmetry. All right, now according to the relativity of simultaneity, he says the offset will be t prime t prime sub a minus t prime sub b equals v sub naught h over c squared. Now this is troublesome because this equation seems like it comes um, from the Lorentz transformation equations, which is really weird thing to do. But let's see let's see what we can get. Um, maybe for a moment, just kind of not really. We'll oh man, I can't draw concentric hyperbolas at all. But let's use a maybe a real Rindler coordinate system. And focus on this point right here, where I need to draw actually I should have drawn that first. Yeah, need to draw the asymptotes first. Take the the Rindler horizon, and then draw the that, and then start drawing the hyperbolas from there. Okay, it's not terribly going well, you can see, but you get the idea. The hyperbolas of the Rindler coordinate system, and this is also the exact same hyperbolas that you would get from the Lorentz transformation itself. Now, with this diagram in mind, I want to see what Stefano Quattrini said. According to the relativity of simultaneity, the offset will be t sub a prime minus t sub b prime equals v sub naught h over c squared. And let me just get let me grab from Wikipedia the equation for the Lorentz transformation for time and or time and distance. Okay, I I think my judgment of this statement is basically false. According to the relativity of simultaneity, the offset will be t prime minus t prime sub b. Um, false. Just the relativity of simultaneity, we would do this. Let's say we've got T prime sub A minus T prime sub B. Okay, so this is uh, T prime sub A and T prime sub B. Uh, he defined earlier, did he define those terms? Uh, he said, okay, I guess he set T sub B sends its timestamp plus H over C to B. So T sub A is plus H over C. Let's do that. T sub A equals plus H over C. So let's just call this um, T sub A equals H over C. Okay. T sub B will, well, T sub A minus T sub B. Okay, so what what are we doing here? There's going to be, we need to really be explicit about where T sub B is. So T sub B prime equals VH, because, okay, first of all, we're looking at a situation where um, B's, where the things are under acceleration. So a lot of the stuff from relativity of simultaneity. Here's what the relativity of simultaneity would say with regards to um, with regards to a set of Rindler coordinates where here, let's say g is the acceleration is, what did we say? C squared over g over x sub a. Here, if we're calling this Rindler coordinate b, then g sub b would have to be equal to c squared over x sub b. And if we call this Rindler coordinate c, we'd say g sub c equals c squared over x sub c. So we're mixing things that shouldn't be mixed, because we've already like discussed these guys as though you can have them accelerating at the same rate and remain in and not be like flying apart in space. But according to the relativity of simultaneity, the offset, um, well, there would be, what offset are we talking about? Are we talking about the offset between the reading here and the reading there, or are we talking, there's going to be, it would really depend on how long that acceleration goes on and all that other stuff. But okay, let me just do this then. If we wanted to calculate, given T1 and T2 are T sub A and T sub B. T sub A and we T sub A and T sub B, and we wanted to find T prime of A and T prime sub B. First of all, note this is going to have to be a time of a certain event, and this is going to have to be a time of a different event, and then this is going to be the same event, the same two event in the primed reference frame. So we could say T sub A is right here. We could say T sub B is right here. And that's fine. We can say T sub A associated with that event and T sub B associated with that event. And then what we would do is basically decide whether we're going to use this velocity or that velocity, this velocity here or this velocity here. We can decide which one of those, if they're, we don't know, they might be the same velocity, they might be a little bit different velocities. And we're going to plug one of those velocities into that equation there. And if we do that, then we'll get t prime. We'll get t prime sub a minus t prime sub b, and then we use the entire equation for both of those. Gamma t minus v x sub a, because x sub a has its own coordinate for that same event, over c squared. Gamma t minus v x sub a over c squared, and this would be t sub a minus v x sub a, minus gamma times t sub b, which is t sub b for this event over here, minus v x sub b, which is the x sub b for that event there, divided by the c squared. And so that would be what you would have to plug in to get t prime sub a minus t prime sub b, where the primed frame has a velocity of v with respect to the unprimed frame. Okay, but yeah, you wouldn't would it come out to be v naught h over c squared? That's a relevant question, I guess. Let's simplify as much as we can. We'll have gamma will come out. It'll be t sub a over c squared minus t sub b over c squared. No, plus, yeah, minus, and then plus, and then we'll take this one because this is minus minus v over c squared times x sub b minus x sub a. So then what else can we say? So we could pull out the gamma over c squared times t sub a minus t sub b plus v x sub b minus x sub a. And then that would be h. So if we said let t sub a equal t sub b and let h equals x sub b minus x sub a, then we would get t sub a prime minus t sub b prime equals gamma over c squared times, this would be 0, because the two t sub a and t sub b were 0. And you would get vh. So how does that compare? Okay, Stefano's statement was, according to the relativity of simultaneity, offset will be t sub a prime minus t sub b prime equals v sub naught h over c squared. The only difference is there is a gamma in that equation, which for low velocities is 1. So, but yeah, so I do still think that the overall statement is just seems false to me. To say that the offset will be t sub a prime minus t sub b prime equals v sub naught h over c squared. This is what you would actually calculate if you specified that t sub a was equal to t sub b. If you specified, and overall the fact that he's said that both of these things were under acceleration during that time kind of removes any, like, you have to qualify that a lot, because this relativity of simultaneity is based on those clocks not being under acceleration. But so altogether, even though I was able to like make a couple of assumptions, define h to be x sub b minus x sub a and let t sub a equal t sub b, and I was able to get the same equation, the same formula. The the prior setup of the problem is not consistent with this calculation, I don't think. Well, looks like my video's gone a little bit too long this time. We'll see if I can stop it and save it, and it'll still work. Thank you for watching, and this is for sound purposes, just to make sure that we get all of the sound into here, where I write ta-ta for now on the screen, just in case some sound issue is cropped up and you won't get to hear everything in the video that's important, unlike this, which is not important at all. Thanks.